In this video, we're going to be looking at series and parallel circuits, and this is the third video of 4 for the electricity topic. So let's get started. So, series and parallel circuits, we've went through this quite a bit now, so you should know what they are, but we'll go over it again quickly. Series circuits are as shown, the circuits where different components are connected on the same wire. Parallel circuits are as shown, they're circuits where different components are connected on different wires. This is really important, this part. There are rules for series and parallel circuits. It's a good idea to learn these off by heart because in the exam, if you're looking at a circuit diagram and you see a junction in that circuit diagram, you've got to think, right, that means something's in parallel. And if all of the components are on the same wire, you can think, oh, that means they're in series. And if you have a very complicated circuit diagram and two components are connected to each other on the same wire, you've got to think, well, they're connected in series. And if two things are connected on different wires, you've got to think, well, they're connected in parallel, okay? So here's the rules for the series and parallel circuits. Series circuits, voltage. Each component has a different voltage. So if you have a series circuit and let's say you've got 3 lamps connected in series in a circuit. Each component will have a different voltage depending on its resistance. So if you have a bulb with a higher resistance, then that will have a higher voltage. So in an exam question, if you're given 3 bulbs connected in series and you're given 2 values for the voltages and you're given the voltage of the battery, well, you can work out the voltage of the 3rd bulb because the voltage entering the circuit will be the bulb's voltage and the voltage being used up by the circuit will be the lamp's voltages. So the total voltage will equal the voltage going into the circuit, the battery. So if you have 3 bulbs in series and you're given 2 of those values for voltage, you can work out the 3rd. So next, series circuits. What about the current in series circuits? Well, each component has the same current passing. So if you have a circuit like this, where you have your battery, or cell I should say, and you have 2 bulbs like that. We're just using bulbs for everything because they're nice and simple and, you know, we know how they work, they make light. So in this case, if you were given the current of this bulb here, let's say this one was 3 amps, there was 3 amps passing through this bulb, and the exam question said, work out the current in the other bulb, well, that's easy. It's going to be 3 amps because it's all on one loop of wire, it's all in series, and the current in a loop in a series circuit is the same everywhere. So the current here is 3 amps, the current here is 3 amps. In a series circuit, the current is the same everywhere. So, parallel circuits. Well, parallel circuits, voltage. Each component has the same voltage. Voltage is shared equally between branches. So if you have a parallel circuit where you have a bulb here and you have another bulb here and you have a battery here, each component has the same voltage across it. That's because this battery here is providing a potential difference across these bulbs. So the current needs to flow from one side of the battery round to the other. So it doesn't matter which path it takes, it has the same potential difference because it's coming from the same battery. So this lamp here, if this lamp had a voltage of 9 volts, and the exam question asked you to find out the voltage of this lamp, well, it's easy because we know from these rules that if the 2 components are connected in parallel, they have the same voltage. So both of those bulbs will have 9 volts across them. Parallel and current. So if you have a circuit which has components connected in parallel, each component has a different current. Current is shared unequally between branches and depends on the resistance of the components connected. Well, we know from the last and the first video in electricity that the resistance is in opposition to current flowing. So if you have a parallel circuit, I'm just drawing the same circuit out again, I shouldn't have got rid of that, should I? If you have the same circuit and you're given that this bulb is 3 amps, this bulb here doesn't necessarily have to be 3 amps. If these bulbs are different, then one might have a higher resistance than the other. If this bottom bulb had a higher resistance, then you could expect that it might only have 2 amps flowing through. And that's because, remember, with Ohm's law, resistance is inversely proportional to current. So if you have a high resistance, the current will go down. So if this bulb has a higher resistance, it'll have a lower amount of current going through it than a bulb of a lower resistance. So in parallel circuits, there may well be a difference in the current depending on which branch you are in, and that's all dependent upon the resistances of those components. So here's a little worked example for you. In the circuit below, determine the current supplied to lamp number 2. Okay, so here we have a battery and we have 3 lamps all connected in series. Well, this one's very easy because we know it is a series circuit, so everywhere in that circuit the current is the same. So 9 amps here, well, there's going to be 9 amps here and there's going to be 9 amps here. So what is the current supplied to lamp number 2? What is the current that the bulb is getting? Well, it's 9 amps. The next thing we're going to go through is the different types of current that there are. There are 2 types of current. Direct current is current which has the same charge all the way through and does not flip between positive and negative voltage. Alternating current is current which continuously flips between positive and negative. This is a quick diagram of the direct current and the alternating current. You can see that the direct current has a constant voltage. It's always positive, or it could alternatively be always negative. The alternating current, that flips between positive and negative potential difference all the time. So at one moment it could be positive, the next moment it may be negative, okay? So that's the difference between direct current and alternating current. The potential difference for direct current is generated by a battery. The potential difference for alternating current is generated by a generator in a power station or something called a dynamo. Developments in science mean new things are discovered. Originally, scientists thought that electric current flow travelled from positive to negative. We call this conventional current. So conventional current is the direction from positive to negative. After the discovery of the electron, scientists changed their hypothesis. As electrons are negative, we now know that current flows from negative to positive. We'll call this electron flow, and this is shown in this diagram here. So on the left we have conventional current. We know that in a cell the longer length is the positive side. So conventional current, as we've just went through, is from positive to negative. So in this circuit this would be anti-clockwise. On the right hand side we'll have electron flow. Now, as we've just went through, the smaller end of the cell represents the negative end. So in this case the current is flowing clockwise. In reality, current flows this way. It flows from negative to positive because we now know that electrons exist. But we still tend to sort of use the conventional current way of thinking in electricity because it's just the norm. It's been used for a long time, and conventional current is it's still the norm when it comes to electrical diagrams. Complete task number 9 in your electricity workbook if you're following along, and pause the video. Right, so next we're going to look at another equation. The third equation that you need to know is that W is equal to QV. Work done, or energy transferred, is equal to charge multiplied by voltage. So work done, that's measured in joules because it's an energy, because remember work done is the same as energy transferred. So that's measured in joules. Charge, that's measured in coulombs. And voltage, that's measured in volts. Worked example. James charges his phone with a 12-volt supply. If an hour's worth of use uses 500 kilojoules of energy, what is the amount of charge that his phone must have? Well, first of all, we're going to write out our formula. W is equal to QV. Work done is equal to charge times voltage. We know that our work done is 500 kilojoules. But remember, kilo means 1,000. So 500 kilojoules is 500,000 joules. We have 12-volt supply, so our voltage is 12. And our unknown value in this case is Q, it's the charge. We want to find the charge. So to find the charge, we're going to divide both sides by 12. So we're going to divide the left-hand side by 12 and the right-hand side by 12 to get 500,000 divided by 12 is equal to Q. If we evaluate this, we get that Q, or the charge, is equal to 41,666 coulombs. And that's because charge is measured in coulombs. So the final answer is 41,666.66 coulombs. A heating element which is 100% efficient transfers 1 kilojoule of energy into heat. The heating element runs on 230 volts and is run for 5 minutes. What is the current that passes through the heating element? Right, this is another one of those trickier questions where we'll have to use two formulas in order to get the answer. W equals QV and Q equals IT. So one way of doing this is to try and find out some value and plug it in, and then you plug that into the other formula. Another way of doing this is substituting one formula into the other. So we know that W is equal to QV, don't we? We also know that Q is equal to IT. Equals means the same. So Q is the same as IT. So what we can do is we can substitute IT for Q. So if we take this Q out and replace it with IT, we get that W is equal to ITV. So this is our new formula that we've created from these other two formulas. Our unknown is the current, it's the I. So what we're going to do is we're going to divide both sides by 300 multiplied by 230. So divide this side by 300 times 230 and divide this side by 300 times 230. So by doing that, we get that 1,000 divided by 300 times 230 is equal to I, the current. Evaluating this, we get that the current is equal to 0.014. Since current is measured in amps, our final answer is 0.014 amps. Complete task number 10 in your electricity.
Thank you very much for watching. Workbooks and test papers which integrate with these videos and online courses are available at our website, backroadtutoring.com.